Syzygy, episode 75, The Story of the Sun. And welcome back to another edition of the Syzygy podcast. My name's Chris Stewart. Joining me from the other side of the globe, way down in sunny New Zealand, is Emily Brunsden. Emily, hi, how are you?
Hello. I'm doing not too bad.
I can see you through the Zoom, and it looks pretty bright outside your window there. And it looks like you've even got the window open.
The sun that comes and visits us down in this strange country.
I wouldn't know anything about that. It's -3 outside here in York, and it's been snowing, which is kind of nice, but I'd rather be where you are. But let's not talk about that anymore. Listeners, look, I know we've had a few pauses over the last couple of months. It's been a bit quiet here in Syzygy land, but we are back and we are committed to doing more. It's going to be great, isn't it, Emily? We've got loads of stuff coming up.
It's so exciting. It's going to be a great 2021.
It is indeed. Listen, before we go on, there's a very, very special person that we need to send a shout out to. Chap by the name of Jimmy Lee, who is our latest Patreon patron, to the tune of supporting the entire website and, web hosting and our domain name and everything. Jimmy has pitched in for the lot. So every single electron that you receive on this podcast, when you go to the website, when you check out all the past episodes, all of those electrons are now down to the great Jimmy Lee. So Jimmy, thanks for coming on board. We really, really appreciate it. All of these contributions from all of our patrons make a huge difference to be able to just do the thing that we do. And goodness knows, when we do finally all open back up again to the world, maybe, Emily, we could do some live shows and go to festivals and stuff again. It'd support all that too.
Remember those good old times.
Remember those days when people could get together and do stuff in the same place? Remember that? In the old times, the pre-times.
We will be back doing that good old face-to-face stuff.
It will come again. But listen, as I said, we are getting back into the swing of it again, and we will be swinging and we will be podcasting, and it's all going to happen. And so to get this underway, today we are going to be talking about, well, something that's been sitting on Emily's whiteboard in her office here in York, even though she's not here in York, but we won't mention that again. On her whiteboard, there's a thing which has been sitting there forever. One of the lists on we must talk about that one day. And it keeps coming up in podcast recordings that we should do a podcast about that, which is stellar evolution, right? How do stars get from being not stars, just sort of gas floating around, to stars that switch on and do starry type things? And then what happens? What do they just go on forever? Do they just explode? Do they burn out and disappear? What happens to them? Stellar evolution. Turns out, Emily, that's a really big topic. There's a lot in that.
It's huge. I mean, I can build you an entire undergraduate course in just that topic alone, if you like.
Right. So when we said what we should do a podcast on that, what we really mean is maybe sort of a short series of podcasts.
Yeah, I think that would be good. We can do some kind of overview-y stuff, and then as and when we want to, we can dive in and do more of the nitty-gritty details as well.
Yeah. Okay. So in the interests of not trying to crowbar too much of that into one episode of the show, which would probably go on for about 6 or 7 hours. Instead, Emily had a really good idea, which was, why don't we start with one star? Why don't we start with a star's evolution? And the most obvious one is the one that's closest to home, which is the sun. So today we're going to talk about the sun, the life of the sun, maybe the life and future death of the sun. I don't know. Let's see how we go. So Emily, if we're going to talk about the sun and its evolution, where it came from, all of that, do we start at the beginning?
I think it would be really nice to tell the story of our sun. So obviously we've got a sun that's here now, and it's kind of a middle-aged sun in terms of its story through its life. So we can go back and give kind of the this is your life version of the sun. This is what's been happening up until now. And then do the kind of go forward and say this is what your life will be.
Sounds like a really, really good idea. Okay, so that's what we're going to be covering in today's show. Before we get there, though, still staying fairly close to home, not the closest star, but at least one of our closest planets. Is Mars our closest planet? Or is Venus our closest planet?
Well, it depends. Maybe we should do an episode on this. On average, the closest planet to the Earth is Mercury.
Oh, okay. Yeah, you ask what you think is a simple question, and it turns out no, it's really, really actually quite complicated. Just park that one for a minute. Okay, next planet out is Mars. The reason I'm mentioning that is because there's a lot happening on and around Mars right now, Emily. There's actually 3 things happening, aren't there? Right now, right at this moment.
Yep, 3 little man-made spacecraft.
Yeah. Here we are. We're recording this on Wednesday, the 10th of Feb. And I just checked the news sites, the interwebs. And apparently, just within the last few hours, the Chinese mission to Mars has successfully entered orbit. And so they've just got there today. The Saudi Arabian mission got there yesterday, and they are successfully in orbit. And NASA's been there for a little while. Couldn't quite figure out exactly when they got there, but their big thing, NASA's big thing, is they're not just going to go into orbit, they're actually going to try to land another lander, Perseverance. They're going to try to land Perseverance down on the surface, and that's coming up in 8 days' time, on the 18th of February. So it's a really exciting time to be a Martian.
It's very cool. Yeah, you're going to get a bit overwhelmed. It's going to be like the paparazzi visiting you or something.
It's going to be very, very cool. And I love the fact that this is the one which, like, Perseverance is the one that's got its own little drone helicopter thing, isn't it?
Yeah. It's got a sky crane.
First helicopter on Mars. Oh, it's going to be just so good. So we thought maybe sort of next, or one of the next couple of podcasts that we record is going to have to be all about Mars and the various missions that have just arrived there and starting to do their thing. We figured we should probably spend a bit of time on that. So that's all coming up. Looking forward to that in a future episode. But for now, let us start with the sun. The sun, this is your life. Emily, where do we get into this one? Do we need to go right back to before there even was a sun? How are we going to find our way in?
Yeah, well, I guess the story of the sun would have to start with the formation. So, how did the sun come to be? And the sun's formation is a pretty sort of standard formation story for pretty much all stars that we have in our galaxy and beyond. And that is, you start off with a cloud of kind of dust and gas sitting around in the galaxy in what we call the interstellar medium, or space between stars. And that cloud, something kind of happens, and that cloud starts to collapse.
Now, when you say something happens, I mean that's a bit hand wavy. So we got a cloud of dust, and then ... brackets, something happens, end brackets, star. So can we just when you say something happens, like what?
Well, we think that clouds can collapse just naturally under their own self-gravity, just because you can get kind of a bit of the cloud which is a bit too dense, and then that starts to gravitationally collapse, and it kind of pulls the rest of the cloud down. But what we also think happens pretty commonly in the galaxy is that a shock wave can travel through this cloud of gas. And, for example, the shock wave from a supernova explosion, which is the death of a very, very large star, kind of explodes. You get a shock wave, and that shock wave can trigger the collapse of a cloud. Right.
So that whichever one it is, whatever the actual causing event is, the idea, I guess, is that a uniform or a very distributed amount of gas is like, that's not an inherently stable thing, because you're gonna get a little pocket here or there that, either of its own accord or because it gets bumped, is a little bit denser, and so that'll start to contract. And if that starts to contract, then it's, the gravitational field there gets a bit stronger, and so it starts to pull other stuff in, and before you know it, you've got a bunch of gas that is collapsing down on itself. So that's the idea.
Yeah, and really excitingly, we actually think that the collapse that caused our sun to form might have actually been a supernova shockwave, and that there must have been a reasonably nearby supernova, because we seem to have all these radioactive elements which are formed that are inside the sun and inside the rocks that are in the solar system, the oldest sort of asteroids and meteors and things.
So you can actually make a guess that's what happened, as opposed to it just collapsed of its own accord.
Yeah, there's some clues
because
there.
Of the stuff that you see around.
That's quite cool, though.
That's cool.
The other nice thing about the sun's formation, so it sort of collapses down and forms. You can imagine it's kind of a runaway collapse, so that it collapses, it gets smaller and smaller and smaller, and eventually sort of isolates itself into a mass which becomes the sun and the planets. But at the same sort of time, it wasn't doing this kind of all on its own. It had some other stars that were collapsing from the same cloud. So you can imagine big cloud, little pockets are collapsing kind of in different regions of that cloud.
Right. That's just corrected my mental image, because I had a mental image which was, a cloud of gas which, in my mind's eye, I'm sort of thinking solar system sized, and there's the sun which collapses down in the middle of that. But you're talking something much bigger than that. You're talking about a cloud of gas which is across, interstellar distances, very, very large distances.
Yeah, very, very big cloud. And then, so the average sort of cloud might form somewhere on the order of a couple of hundred stars for the smaller ones, and then up to thousands for the very, very big ones.
Right. Okay. So that's, I've just upped my my mental image of what we're talking about here. Good.
So, I mean, one thing you can say is that we had some sister stars that were forming at the same sort of time. And that might be a sort of a new concept, because we don't often talk about our solar kind of siblings. But I thought it worth giving a quick mention, because so what tends to happen is once you form, the sun is orbiting around the center of our galaxy. And it's orbiting at a particular speed or rate around the center. But depending on where you sit in terms of radius from that center, so if you're a little bit closer to the center, then you go around at a different orbital speed than if you're a little bit further out.
Okay.
And so the effect of that is that actually, even though all the stars can be born from the same cloud, if they're not sort of very tightly gravitationally bound, then their natural kind of wandering around the center of the galaxy means they all separate out over time.
Right. So even though initially they would have all been fairly close, it's all been smeared out now. So do we have any idea at all what our sibling stars might have been? And if so, how?
Well, excitingly, we have found one definite, probably, and one possible sister star. So we've got HD 162826.
Yeah, attractively named, yeah.
Yeah, we think might be one of our sisters. Now, that's actually quite a close star. It's only about 110 light years away, which is sort of solar neighborhood.
I'm slowly but surely figuring out in my own brain that, that's actually reasonably close by local neighborhood standards.
Yeah. And so the reason why we think this particular star, out of all the others that you can sort of, see around us, might be a sister, is because it actually has a almost identical chemical makeup to the sun. Right.
So, that obviously was going to be my next question, is how the hell do you know? But if you're looking for something which is made from the same stuff at roughly the same time for the same reason, i.e., maybe the supernova or something, then it's going to look a lot like our own sun in composition.
Yeah. So all the different chemical elements that you can find in the atmospheres of these stars, and sort of the ratios of those particular chemical elements are going to be the same.
So the fact that it is still relatively close by, does that mean that it is then gravitationally bound in sort of the same, star cluster that we are? Or is that just coincidence? Or why isn't it miles away?
So in this case, we think it's actually just probably coincidence that the star is kind of that close at the moment. It's not. There's no link gravitationally between the sun and this one. So we just kind of either lapping each other, or just happen to be in a similar point in the orbit and around the galaxy.
Wow, that was lucky. So, but you said that there were two, and so that one's the fairly definite. We're pretty damn sure that was a sibling.
Yep.
And then there's another one which is, maybe this one too.
Yeah, so in 2018 we actually found another one called HD 186302.
Mm-hmm.
This one's slightly further away.
But again, the composition, very similar?
Composition is looking like it's pretty much the same, yeah.
Very cool. Well, congratulations, son. You've got some... That sounds really weird, doesn't it? Son, you've got some siblings. Anyway, the star might have some siblings. That's very, very cool. Okay,
yeah.
So that's kind of looking at the very earliest stages of where it came from.
Yeah, so I guess you can try and define the moment when a star becomes a star instead of a cloud of gas.
Right.
Now, there's different ways you can think about it, but I think probably the most intuitive way is to say, well, a star becomes a star when you've got fusion turning on inside the star.
Yeah, that feels to me like a reasonable definition of when stars become starry, is when they start doing things that stars do. When stars have fusion going on inside, which makes them shine. So when the star starts shining, that's when it's a star. I'd go with that. Yeah.
Yeah.
All right.
So I guess you could think about gestation as being a little bit like the cloud collapsing, collapsing. We've got a lot of ways that we anthropomorphize our...
We should probably
our
just not push that analogy too far. We'll get into trouble with that one. But yes, okay.
Well, yeah, I mean, you say that, but actually we do tend to use language around stellar evolution, which is a bit the same language as life cycles. And I got told off for doing that a couple of years ago because they said the primary school students would get very confused about whether stars were alive or not, because we talk about, stellar birth and death and things. And I thought, you know what, they're going to become great astronomers. They need to know these terms, because
come on,
my
kids,
colleagues
toughen up. You're going to have to,
yeah.
That's lovely, though. I'm now imagining a whole bunch of weeping, primary school kids at an Emily talk. I think that's hilarious.
Yeah. So, gestation. We've got the collapsing cloud. As a gas cloud collapses, it's getting warmer and warmer and warmer as you're compressing. And once you hit this kind of sweet temperature of somewhere around 10 million Kelvin, then you start have fusion. And there's different kind of fusions that start, but eventually you do get core fusion, which is the kind of hydrogen to helium main fusion reaction that we all know and love.
And at that point, like, there's a transition going on in my mental image of this, which is cloud of dust collapsing down, but it's still sort of looks like a cloud of dust. And at some point, it's got to become a ball. I mean, the sun is a ball, Emily. It's a sphere. So, has that happened before the fusion switches on, or is that?
Yeah, it does. Actually, happens very quickly, because what happens is your cloud will not be kind of a static cloud. There's all the molecules of gas and dust have some kind of motion inside that cloud, and because of that, there's some kind of net overall motion. And for a very large cloud of gas and dust, it's almost imperceptible that you've got this kind of overall rotation, let's say, of the cloud. But due to the conservation of angular momentum, our good old friend piece of physics there, when you collapse the cloud down, as you collapse it, that rotation gets faster and faster and faster. And so that helps to pull everything into a spherical distribution or shape.
Right. Okay. So you've got your ball being formed, but as it's collapsing down even further, it gets hotter and hotter and hotter. And what did you say about 10?
10 million Kelvin, yeah.
10 million. I was about to say 10,000. I thought, no, it's warmer than that. 10 million Kelvin, which is warm indeed. Then the nuclear reactions, the fusion reactions, turn on. And is that the simplest fusion reactions? Is that the hydrogen? Or if there's other stuff around, does that switch on first?
Yeah, you can get some other sort of earlier fusion ones. So when we talk about, for example, failed stars, they can have some very sort of low energy or lower energy fusion with deuterium, so heavy hydrogen and things like that, at lower temperatures.
Right. So failed stars, is that where the engine didn't quite start? It's kind of kicked over a couple of times and then went quiet.
They got kind of warm, but they didn't sort of set up their fusion cores like the sun or bigger stars.
Right. But the sun didn't fail. It started up proper. The engine got running. And so what's going on at that point?
So I think we've talked about planet formation before, so I won't really go into the details of it. But at that time, then the sun's switching on, you've got already a disk of material, which is also formed by the same principles of conservation of angular momentum. It means you've got a disk, and then your planets are sort of forming in that disk at this time. But once the star turns on, it sort of blows away any excess material, any of the lighter elements that were sort of floating around in that disk.
Okay, so it turning on is a fairly violent affair? Is it sort of a sudden and violent affair? Yeah.
Yeah, I mean, think about the solar wind, which is this kind of constant stream of charged particles coming off the sun today. In the very early stages, when the sun was kind of settling into its fusion reactions, that would have been much, much stronger and more violent and more probably irregular as well. So you kind of get this, a little bit of a sort of jumpy start going.
God, that must be a thing to see. If you could be around to see it, that must be a hell of a thing to see. Is this, what I'm imagining is an enormous bomb going off in the middle of this brand new system?
So I guess then we sort of reach what some people might call the boring bit of the sun's life.
It's been fun so far.
So that whole process will take place over, a few tens of thousands to maybe a few 100,000 years. So it doesn't take a super long time.
That's pretty quick, considering that the sun's been around at this point for how long?
About 4.5 billion years.
4.5 billion, and we're talking in the tens of thousands of years.
Yeah.
So that's real quick. We've gone from not a star to we now have a star in a pretty quick period of time.
Yep.
Okay, cool.
And so the reason why the next sort of phase of the sun's life, which is including where it is now, is called the boring bit, is because this is where it kind of just merrily fuses hydrogen to helium, kind of stays pretty much the same over the whole period of its life, and it's going to be the longest period of its life. About 90% of the sun's life is going to be spent doing this kind of fusion hydrogen to helium over the course of maybe 10 to 11 billion years.
Right. So down there in the core, there's a whole pile of hydrogen, and it's being squeezed and fused together, and out spits some helium. And it just keeps doing that for a really long period of time. So either it's got an enormous amount of hydrogen, or that process isn't as fast as I imagine it is. Which one is it? Is it that there's huge amounts of hydrogen and it's all fusing, there's an enormous amount of it fusing all the time? Or is it actually one of those weird astronomical things where, well, Chris, you'll be surprised to learn that actually the rate that hydrogen gets burnt in the core of the star is actually fairly slow?
It's definitely the former. Because
Okay.
if you want to know how, with the rate of hydrogen fusion, you're looking at going through something like 4 million tons of hydrogen being converted to energy every second in the sun.
Every second? Okay, so it's definitely not the latter. It's definitely the former. There is a metric truckload of hydrogen in the sun, which I guess makes sense because it's very big. But
The sun is quite large.
Yeah, I've learnt quite long ago to just, not pay a lot of attention to what my intuition tells me about astronomy. So, you could have told me that it was the latter of those two possibilities. Yeah, there's not a lot of hydrogen being burnt at all. And I would have believed you. But turns out, no, actually quite a lot.
There's an awful lot of hydrogen.
Yeah.
So I think it adds up to something like 100 times the mass of the Earth has been fused. And hydrogen has been fused over the course of the sun's life so far.
That's quite a lot.
So it's about halfway through this sort of boring bit, that what we call the main sequence phase of its life.
Right. And
So
it's
100
got
times the mass of the Earth
billions of years to go.
Yeah, well, as I say, we're only about halfway through the fuel source,
Right.
basically.
Right.
At least the fuel that's available to it in the centre. But all of that, just to reassure you that we're not going to run out anytime soon, all of that 100 times the mass of the Earth only adds up to something like 0.03% of the mass of the sun.
Okay. All right. So this is not a problem that we need to worry about.
It's all good.
This is not.
It's
It's not
plenty.
going anywhere anytime soon. So I'm fine with that. So at the moment, we are both narratively and quite literally at this epoch of time. In this boring phase, in the main sequence phase of our star, it's the boring phase, but I mean, there's stuff going on. It's not just sort of sitting there doing exactly the same thing all the time. So, tell us a bit more about the boring phase. What does the sun do during all of these billions of years?
Yeah, so it does change a little bit. It's just, I guess, nothing so much as the dramatic changes that we're going to talk about post today. But yeah, so it's gradually going through this hydrogen, it's fusing this hydrogen to helium. The helium, what we call ash, because we're very naughty astronomers, we talk about fusion reactions as being burning reactions, despite the fact there's no flame, there's no fire.
I love
So
it.
we
I mean,
sometimes-
everything
yeah.
other than hydrogen and helium is a metal. And when you burn hydrogen to make helium, you get helium ash. You're very simple people, aren't you? There's hydrogen and then there's ash and there's hydrogen and helium and then there's metals. And it's like life as an astronomer must be so uncomplicated.
Yeah. No.
Or is this just compensating for all the complications you find everywhere else?
Possibly.
We need to
yeah,
simplify where we can. Simplify where we
Yeah,
can.
yep. Absolutely. Approximate and simplify. But yeah, so we do have this helium ash, which is kind of building up into the core. So if you imagine helium's a little bit heavier than hydrogen, so you can sort of think about it as sinking into the middle whilst of the core, and that's fusing hydrogen. And what that actually does is it means that the bit that's fusing hydrogen is actually growing a little bit. So the fusion core is gradually growing. Not, very fast, but very slowly. Which does mean that actually the temperature of the sun is very slowly increasing.
Okay.
And the brightness is very slowly increasing. So I think our current estimates are something like we've increased by about 30% in brightness since the sun sort of started fusing.
Okay. So again, when we're talking slowly, we're talking over billions of years.
Yeah.
It's not something that we're going to sort of notice in our lifetimes, or indeed the time that our species has been on the planet. It's a really long period of time.
Yes, you absolutely are not allowed to blame the sun for global warming. It is
Good.
not its
Strike
fault.
that one off. Good. You heard it here. That's enough of that nonsense, people. Okay. So, but you've also got the sun is changing over a sort of time scale of like years and decades, though. Like not in a way that can explain global warming, but it does have cycles and so on. Like it is doing stuff, albeit in a way which is not going to threaten our species so much.
Yeah, absolutely. The sun has its own kind of magnetic cycle, which runs over a 22-year period. So it flips its magnetic axis every 11 years. And that's why we have kind of periods where there's lots of sunspots and periods where there's not. We should definitely talk about that if we haven't already. I have to remember if we've talked about it.
I don't think we have. And it sounds very exciting. Like something the size of the sun flipping its magnetic axis. Like that's an event you want to see. You want to capture that one. That does sound like the sort of thing that would spell the end of a planet like Earth. Like, surely that's going to just knock us out of alignment. Apparently not, because every 11 years we would have noticed that. But that sounds big.
Right. I will get the photo that I have of the whiteboard that's in my office, and I will Photoshop that topic onto it.
Okay. Park that one for a future episode.
I'm not allowed to be there physically.
Future episode, we're going to talk about the sun flipping its magnetic axis, because that sounds awesome. Okay. Leave that aside for a second. That's a whole other podcast.
So I guess there's just this gradual increase in the luminosity of the sun is kind of the bottom
very
line.
Gradual.
Pretty much all it does on the main sequence.
Cool. Okay. But as you say, boring in terms of, large scale dramatic stuff. So when do we get back to the large scale dramatic stuff? When does the boring phase, because it's a phase, right? When does that end?
Well, I guess depending on which way you want to look at it, it could be good news or bad news. If you like living on planet Earth, then I guess the good news is you've got about 4.5 to 5 billion years to go.
Okay, so a bit of a moot point, but let's go there anyway. What happens in 4.5 billion years, if I'm around to see it?
So this is when we start transitioning into the next phase of the sun's life.
Mm-hmm.
Effectively, you start to run out of fuel, out of hydrogen fuel in the core of the sun. And this is where it gets a little bit more exciting. I mean, it's worth mentioning that Earth will become uninhabitable before then because of this gradual brightening of the sun. I mean, estimates vary, but you've got maybe 2 to 3 billion years left.
Oh, right. Okay. So we'll just scale back our ambitions by a couple of billion years then.
On Earth.
Yeah. Okay.
But the actual transition to a new phase will happen in 4 to 5 billion years. And this is what we're going to call the red giant phase.
Oh, that doesn't sound good. Because the sun's like a relatively small star, isn't it? Isn't it sort of a fairly small yellow common or garden variety star?
Yes, it's slightly kind of under average in terms of the range you can have for stars.
In fact, isn't it even called a yellow dwarf? Isn't that what kind of star it is?
Oh, yeah. You've got to be very careful with dwarf, though. That's another naughty astronomy thing.
Really?
Yeah.
Okay.
All stars on the main sequence are called dwarfs, whether they're the size of the sun or 20 times the size of the sun.
Well, that doesn't make any sense, Emily. You can't just take all the stars and call them. I mean, the term dwarf star implies smaller brackets than average end brackets, and if you've got all of these stars which are in the main sequence, then how can they all be dwarves? Pull your socks up.
Well, they're all smaller than the red giants that they will become.
But look, I'm just going to have to let this one go. But at some point, you and I are really going to have words about the way you lot call things, okay? But let's move on.
Can we agree that red giant is a nice term for something that's very, very large and very, very red?
I have no problem with you calling something that gets really, really big a giant. That's fine. My problem lies elsewhere, but let's leave it for now. The point is the sun is a relatively small yellow star for most of its life, and then it turns into a red giant, which sounds scary.
Yeah, so what's happening is a kind of an extension of what the process we had before. The fuel's running out in the core, so that kind of fusion has to kind of move further and further out, and actually the rate of fusion starts to increase. So it's almost a runaway process. Stars are a delicate balance between the gravity that's trying to collapse them down and the energy that they've got to produce to hold themselves up.
Right.
And it's at this point that sort of starts to tip over.
Now, we've talked about this on the podcast before, but let me see if I can reconstruct it in my mind. You've got gravity pulling down, right? All the bits of the star, all the gas, all the plasma, all the stuff, it's all pulling on each other, and they're all trying to pull down towards the center. But as you do that, you heat up because everything's sort of bashing against each other. And you keep heating up and heating up and heating up. You turn on these nuclear fusion reactions, and the energy released from that pushes outwards. And so you end up with this balance, which is, no, we're trying to pull into the center. No, we're trying to push apart. And whichever one of those wins means, if it's pushing out, wins a bit more, then it cools down a little bit, so it pulls in. And you get this balance of pushing out and pulling in. What you're saying is that as you run out of one of the fuels, if you run out of hydrogen, then you upset that balance and it has to find a new balance point, a new equilibrium, because the push out and the pull in is different.
Exactly.
Right?
Yeah. And so this is why you can have red giants are a little bit of a conundrum in a sense, because you've got a star that's doing more fusion, yet it becomes bigger and it becomes brighter, but the surface becomes cooler.
Okay, hang on. Bigger, brighter, but surface is cooler. Work me through that one. How does that work?
So that's just because you pushed out the surface, so it's become more rarefied. So it's a little bit like if you expand a gas, that you can cool the gas down once it's expanded. And so that's what's turning it red. So our sun, we can sort of think about it as being a yellow-green color, then as it expands, just the surface cools, and that's what makes it a red giant.
Yes, yeah. Because we tend to associate red with, red hot and so on. But of course, you go beyond red hot and you get to yellow hot, you get to white hot. Eventually you get to blue hot, which is really, really hot indeed. So red is just the coolest of the hot things.
Exactly. So if you want some cool stats,
we all do.
Cool stats about the sun, so that we understand from our models that the sun is going to go from being approximately 0.01 astronomical units in size at the moment.
Okay, astronomical unit 1%. Distance from the sun to the Earth. So 0.01, so that's 1%, did you say?
Yep.
Okay, of the distance from the Earth to the sun is the sun.
Well, it will be about the size of the sun when it's finished its main sequence phase. And it's going to push out to being about somewhere around 1 to 2 astronomical units during its red giant phase.
Oh, sorry, and is that radius or diameter?
That's radius. So
So if the distance from the Earth to the sun is 1 astronomical unit and the radius of the sun is going to be 1 to 2 astronomical units, then Earth's not going to be a terribly good place to be anymore, because it's going to be literally inside the sun.
Exactly.
That's not good. That's no way to run a solar system.
Yeah.
That does,
No, it's maybe not the greatest place. I mean, the sun's also going to be brighter by about 2,000 times. So.
Oh. Well, I mean, it would be, because it's literally right there, like it's knocking on your door,
Well, I mean, this is the intrinsic brightness, so it doesn't matter what the distance is.
So it's not even the fact that it's like, staring in through your window bright. It's that it's also a lot brighter.
Yeah.
Right.
You're upping the wattage on your light bulbs, if you like. By about 2,000 times.
Good thing, though, is that your solar panels will be going absolutely berserk by that point. So, win-win, really.
Yeah, I mean, the good news is Titan actually starts to become a really good place to go live.
Oh, okay. Well, we could just start moving further out then. Once Mercury goes, we'll take that as a sign. Yeah, look, might be time to move on. Head out to Mars for a bit, onto Titan. Titan is one of the Jupiter moons, isn't it?
Saturn.
Oh, we've gone well past Jupiter by that point. Yeah, okay.
So, perks and
of
the business. Yeah. So the Earth is probably not going to be great at that point.
No. So, question, how long does it take? Like, we've had billions of years of the boring phase. You get to the end of the boring phase, and then the sun goes, well, I've run out of that fuel. I guess I'll start doing this thing, and it starts puffing up like a blowfish. How long does it take for, let's say, for the sake of an argument, the sun to go from small yellow thing to big red thing the size of the orbit of Earth? What's that period?
So the whole red giant phase of which it's sort of growing is over the course of about 1 billion years.
Okay, so that's not super, super fast, but in terms of how long it's been around, it's a relatively small chunk.
Yeah, exactly. So then what's happening, I guess, inside the core becomes really interesting. So your core hydrogen fuel is starting to run out. It's somewhere like around about 5.5 billion years now from now.
Mm-hmm.
So the red giant phase sort of kicks in, and then eventually the core hydrogen does actually totally run out. So then you're just left with this helium ash in the core, and then you've got this shell of hydrogen fusion, which is happening around that core. But of course, what's happening is you're now dumping heat into the core from the shell, because the core itself isn't fusing, and that core is also collapsing down because you've got heavier helium, which is contracting, and you've got the shell, the collapse of the gravitational pressure from the star, sort of all collapsing that shell. So the core.
So there's a lot pushing down on that core.
Yeah. So you're crunching down, and you eventually get to a point in structure where you can't compress the helium core anymore.
Okay.
And this is a point we call degeneracy. And you're probably an expert in degeneracy, actually.
Well, if I remember back, because it's been a while, Emily. I mean, let's not say expert, let's say vaguely familiar with. But when you start trying to push atoms, particles together, then there are certain things that they just won't do. There are things that particles just will refuse to do. And one of them is that, at least for many kinds of particles, and most of the matter particles fall into this category, is that they will refuse to be in the same state. You can't have 2 protons or 2 neutrons or 2 electrons sitting right on top of each other, being in the same place, doing the same thing at the same time. And this is the thing which basically makes atoms the interesting structures that they are. That if you've got one electron doing another thing, add another electron, well, it has to be doing a slightly different thing, and you end up with interesting stuff that gives us chemistry and everything else that we see around us. And so if you squeeze this down really, 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 really tight, you're going to reach this limit where the atoms are so close together that the laws of physics themselves are saying, look, I'm sorry, I've got nothing left for you. You can't get any closer, because that's what quantum physics allows you to do. This is as far as you can go and still be allowed to exist in the universe. So that becomes a pretty solid endpoint, I guess.
Yeah, exactly. Yeah. So we call this electron degeneracy because it's the electrons that you can't squeeze anymore. So the electrons are all squeezed up kind of as close as they possibly can, the closest even quantum mechanics allows them. So you've got this really tightly packed core. So even now, if you're dumping more temperature into this, dumping more heat into the core, then it's getting hotter, but it's not changing in size.
Right.
So it's just this really dense ball that's now just heating.
That feels to me like a relatively unstable situation, Emily. I kind of feels like a bomb waiting to go off at that point.
Well, you're quite right.
Funny you should mention.
Because you do eventually get to the flash point for helium, which is the temperature at which helium fusion sort of switches on. And what's really exciting is because this whole core is degenerate, it means that you only need one atom of helium to flick to start to fuse, because it's reached the critical temperature for helium fusion. And then almost instantaneously, the entire core just all erupts, all ignites at the same time.
Wow. That's got to be a thing to see from a safe distance. Like you'd want to stand back for this one. It's a little bit like, don't go too close to the firecrackers on bonfire night. You want to step right back for this one. But kids, you got to keep your eyes open. You're going to want to watch this. It's near the flashpoint. This is going to be wild. That sounds amazing.
Well, it's very cool, but I'm going to disappoint you as well. So
really?
we call this the helium flash, and it is this instantaneous blip, and the whole core just goes up all at one time. We're starting to fuse helium to carbon at this point. The disappointing thing is that actually, although we call it a flash, and it is a flash in the core, the surface actually takes maybe a million years to start to react to the fact that something's happened in the core.
A million years? Hang on, but light travels a lot faster than that, Emily. Like, the sun's pretty big by this point, but it's not a million light years across. So that's how? Why doesn't
we can parallel this with what's happening in the core of the sun. So if you create a photon in the core of our sun through the fusion of hydrogen to helium, if you did that right this second, it would actually take 100,000 years for that photon to leave the sun.
100,000? Like now?
Yep.
100,000 years. That's absolutely nuts. Okay, so is this because there's a lot of it's an obvious statement. There's a lot of stuff in the way, right?
Exactly.
Between the core and the outside of the sun. So what's happening? I mean, is it that energy is getting absorbed and then re-emitted and absorbed and re-emitted? And like, I can imagine that, but I can't imagine 100,000 years of that. That's absolutely nuts.
Well, you're exactly right. It is this constant absorption and re-emission, and the fact that photons don't actually travel very far before they hit another atom, get absorbed, then they've got to be re-emitted. But remember, they may not be always re-emitted. In fact, most of the time they're not re-emitted, such that they're traveling towards the surface still. They can be re-emitted, so they're heading back into the star. It's a random process, so it can happen in any direction. So they kind of have this little journey. We call it a random walk, where the photon kind of
just wanders around for 100,000 years before eventually going, oh, here I am, popping out of the surface and making its way across the cosmos. So with the helium flash, how long did you say it would take before we would see it? If we were there,
all the energy it dissipates quite slowly over the course of a couple of million years. So there's no optical flash. So although you've got the flash in the core that's happened, it just sort of, it takes a long time for the atmosphere to register, if you like. And It doesn't all register in a single event. It just sort of slowly leaks out.
What an amazing concept. That's got to be a hell of a lot of energy, I'm guessing. And yet, if you were to watch it from the outside, is it? No, nothing. No. Maybe wait for a while. You might see a little something in a couple of million years. Cool. Okay. So, but this means now that the helium is fusing down in the core. And you said it's fusing to carbon. And I mean, this is the really interesting thing about all these processes is, we've turned on the hydrogen and then you run out of hydrogen. Well, what do we do? Oh, we've got no hydrogen to burn. But that's all right, because we just have to wait, because when it gets hot enough, something new happens. And so we burn. Did you say we burn all the helium like pretty much at once? It's really quick, or is it just it all turns
ignites.
on? Right.
Yeah,
okay.
The whole core ignites. But yeah,
Gotcha.
so this is it's interesting. I always think about this sort of part of a star's life as it's kind of desperate. It's like, okay, I've run out of hydrogen, but I've got to hold myself up. What am I going to do? Oh, hey, I've got some helium here. Let's
grab the helium.
That.
Go.
Yeah, go. Yeah, we can fuse that to carbon, maybe a bit of oxygen, and then actually in larger stars that process continues until it just tries to grab whatever it can fuse. So the core temperature at this point is about 350 million Kelvin. So it's a pretty hot core.
That's pretty warm.
And it means that fusion of the helium is actually very quick. I mean, in terms of sort of larger timescales, it doesn't take super long for it to start chewing through that helium.
Okay. When you say not super long, as in like rough timescale?
Probably got something like on the order of 100 million years.
Okay.
Where this helium fusion can kind of restabilize the star and sort of say, okay, we were running out of that stuff. We were on this horrible runaway trajectory. The helium flash actually almost like pulls the star back to like, okay, it's okay. We're going to be all right.
It's all right.
We've got this helium. We can pretend that we're on the main sequence again.
Got another couple of 100 million years. We're okay. We're all right.
Yeah.
We're all right. But I mean, we've gone from 10 billion-ish years of the boring hydrogen burning phase now to, what did you say, hundreds of millions of years of helium burning? Okay, so that's like order of magnitude or two lower. Then what?
So the star's always shrunk down because it's almost like it's back. It's trying to get back to the main sequence. It's trying to be like, yeah, let's go back to normality. So it's shrunk back down to being just about an zero point 0.1 astronomical units. So
Okay, so that's small again. Wow.
yeah, it's shrunk quite a lot. It's now about 2,000 times the luminosity it is at the moment. Then it's maybe 50 times. So it's all kind of restabilized.
Does it go back to being yellow again?
It will become warmer, but maybe not as hot as the
Right.
current sun. So I can't remember what the exact temperature is, but it'll be
Orange.
in between.
Yeah.
In between. Yeah. And we call this the horizontal branch, or it's this kind of second bit of life. But as you say, the bad news is this is only going to last for about 100 million years.
Mm-hmm.
And this is when the helium starts to run out, and you've got sort of episodes of helium fusion. You've got this hydrogen fusion still happening in a shell. The relative ratios of those sort of get out of balance, and they can start to disrupt the entire star. And so we move into kind of a much less stable phase where the sun starts to go through these kind of thermal pulses. So it's got sort of periods where it gets brighter and it sheds a lot of material, and then it sort of cools down a little bit, and then it gets brighter again and sheds. And these aren't really regular. They're just kind of dependent on the chaoticness of the fusion that's going on, trying to manically kind of keep the star going.
So that sounds like a fun phase. Okay, a lot going on there. Then does that mean that it's like, is it sort of, growing and shrinking and stuff along the way as well? It's just all over the shop.
Yeah, so now after this 100 million years of the sort of helium fusion, then you've only got about 20 million years of thermal pulsing, where it maybe gets as big as a 1 AU, so out to the radius of the Earth's orbit, about 5,000 times the luminosity of the current sun now, so really bright. And with each of these pulses, it's throwing off enormous amounts of material, so it's really unstable. It's ejecting its atmosphere into kind of the solar system.
And that's a really short time frame. Like you said, 20 million years? Like that's
20 million years.
That's a really short time frame for something as big as a star to be ballooning out to that kind of size. Like that's a lot.
Yeah, so by the end of that sort of 20 million years, between all the other processes, it's been slowly losing mass. The sun's been slowly losing mass all the time through the solar wind, and even in the red giant phase, it loses a bit of mass. So, but this is the real mass loss period, and by the end of that 20 million years, you've probably only got about half the mass of the sun left.
Wow, okay. So what happens to that half?
Well, the half that is kind of already shed off is it's just dispersing, and then the remaining half actually is sort of the fusion sort of just starts to peter out as you become more and more rarefied, because then you're cooling your inner regions as you're kind of the atmosphere is cooling, so the fusion just starts to kind of drift and die off, and eventually all that atmosphere is it's being pushed off, it's been drifting away, and it's actually that atmosphere that becomes one of our favorite types of nebulae that we have to look at through telescopes, which are planetary nebulae.
Oh, right. Gives an example of a planetary nebula that I might know and that the listeners might know.
The Helix Nebula is quite popular, or the Cat's Eye Nebula. These are really nice planetary nebulae to
I know those
either
ones.
look at through pictures
have a look
on
at
the internet or
have a look at your phone or your podcast player of choice, because there's a picture of one of those on your screen right now.
the magic of the internet. Yeah, and as planetary nebulae, confusingly again, nothing to do with planets. They're just the atmospheres of these kind of old stars like the sun.
Yeah, why were they called? I remember you mentioned this once. Why were they called planetary nebulae? Because people thought that that's where planets came from, or something.
Yeah, I guess they were linked to stars, so they sort of thought this might be the early disks of planets. Or
right,
and
like they got that completely wrong, because it's actually the end.
Very wrong.
Yeah. Okay. So the sun at this point, it's lost a hell of a lot of its original mass. It's gone a bit nuts, wobbling backwards and forwards. But I get the sense that things are now going to start to just go a bit quiet. What happens from there?
Yeah, so you've kind of got the atmosphere that's drifted out and become this planetary nebula. So all that's left at the end is this kind of hot core. And this core is made up of the carbon that was, fused from that helium fusion reaction. Little bits of other bits and pieces. You might get a bit of oxygen, for example, as well. And but it's almost like you're kind of lifting the veil of the star, because now you can the atmosphere is so rarefied that you can see into the very, very center, and you're just seeing this leftover core, which is what we call a white dwarf.
Ah, right. Okay. So it's still fusing at this point, and
so the fusion's pretty much stopped now. We've kind of run out. We've run out of stuff.
So it's just sitting there glowing with its heat, but presumably that's just going to cool down over time. And
exactly, yeah. Well, it starts off with crazy temperatures. So we're starting off with this core at kind of a couple of 100,000 Kelvin.
Yeah.
But then that's all that.
Hence white dwarf, right? It's white hot.
Yeah.
Yeah.
And all that energy is going out into the atmosphere of what was its atmosphere, which is now the planetary nebula, and that's what's actually making it glow. It's the light from the white dwarf interacting with the leftover.
Oh, right. So all of the gorgeous colours in these really well-known nebula images, that's coming from the extreme heat of this tiny little white dwarf that's left over.
Yeah, so it's sort of putting out photons that can go and interact and, have lots of different transitions in that.
So how long does that last? Because if it's not fusing anymore, it's not making any more energy from the nuclear processes. So it's going to cool down. How long does that go on?
Yeah, well, it only takes about 10,000 years for the white dwarf to cool so much that there's now not enough photon energy to illuminate the planetary nebula.
Right. So what you're saying is all of the nebulae that we see that are of this type being illuminated by their white dwarfs, we're only seeing those because they happen to be around at this point in time. Like we're catching them within that sort of 10,000 year period. And if we were around sort of, 10,000 years from now, they wouldn't be there. We'd be seeing other nebulae in other places in that place.
Yeah, they're quite fleeting objects, really, which is quite interesting.
Okay. Yeah.
The white dwarf, however, is going to just carry on cooling down and cooling down and cooling down until, some of the white dwarfs that we sort of measure around 30,000 Kelvin, things like that. But eventually they will cool so much that they become what is, I guess, still technically a hypothetical object, but would be a black dwarf.
Right. So hypothetical in the sense that we've never seen one, presumably because they're black. They're not shining anymore. They're not hot. We can't see the light coming from them. So we just assume they're out there?
Yeah, well, it also would take a really long time. So that just means you're cooled down to kind of the ambient temperature of the interstellar medium around you, if you like. But that's going to take longer, I think, than the universe has had to run yet to get to that temperature.
Okay, so, really long time. So it's not like the universe is out there full of, dead white dwarf stars that we don't see anymore. It's that, I guess, in principle, that's where we'd get to eventually.
Yeah.
Yeah, right. So our sun is not going to go out with a really big bang. We're not talking sort of supernova here. We're talking a pretty sort of nasty, petulant end, and a nebula, which is kind of cool. That'd be nice. And then just slowly but surely cooling off over a very long period of time and fading away.
Yeah, it is kind of a bit of a sad, slow, quiet, pretty ending.
Yeah, but I mean, that's not bad. That's kind of nice. Like, at least you got the nebula, right? If you didn't have the nebula and you just sort of, well, I'm here, I'm really, really bright, but I'm just going to slowly fade away, that'd be sad. But it's nice to have a nebula around you that kind of marks where you were. I think that's good. Yeah, nice one.
And I guess to give you a sort of sense of the timescales, if you reflect back over the whole life of the sun, that whole process is somewhere in the region of maybe 11 to 12 billion years. That's the whole life
from
of
beginning
the sun.
to end. Yeah.
Yeah, and if you remember, our whole universe is only about 14.7 or so billion years old, right?
Yeah.
And the sun formed about 4 or 5 billion years ago. But even if you sort of play, like, the first stars didn't form instantaneously when the universe started. It took a while to get them up and running, and then the stars' length of time that they're alive is dependent on their mass. So if you are a big star, it turns out you go through your fusion very quickly and finish up your life very quickly. But if you're a little star, then it takes a really long time. I mean, the sun's already, got 12 billion years of life. If you're smaller than the sun, it's even longer than that. And the upshot is that we can say that every star that has a mass of about 80% of the sun's mass or less that's ever been born of those low masses is actually still alive today.
It's still out there. Yeah. Because our sun is, it would be because you said that it was probably formed from a supernova from a previous star. So it's at least second generation, maybe more?
Probably much more than that, yeah, because of the number of sort of these, when we talk about high mass stars, they go through a lot more fusion to get lots of really interesting metals, interesting larger chemical elements, let's say, and that we can see those formed in the sun.
That's potentially a story for another time, because that's more stellar evolution that we got a whole other podcast, Emily, to get to on that one. But yeah, so you're saying that the ones that are smaller than the sun, formed right at the beginning, they're still around. They're still kicking. They're doing their thing, and will be for a very long time.
Yeah. So if you want to live a long time as a star, you want to actually be the smallest mass you can possibly be.
Yeah. Keep your head down and just, stay out of trouble.
So the good news is with this planetary nebula that's kind of gone out there, even though the planetary nebula sort of fades away and it's not bright anymore, it is going to be recycled into the next generation of stars.
Is that analogous to where our sun came from? That we would have come from a planetary nebula or some sort of, end of life equivalent from a previous star?
Yeah, it turns out that galaxies are these great recyclers. So once you've sort of injected all your material from the atmosphere of these stars, that will go out into the interstellar medium. It will mix. It will form with different clumps of gas and dust that are out there, and then it's those clouds that will go on and form the next generation of stars.
But doesn't that also mean that the next generation of stars that come after the sun, it's going to have a whole mix of stuff in it? I mean, presumably, as our sun already does. Does that mean that stars are sort of getting more and more mixed up with heavier and heavier elements and all sorts of weird stuff over time, that they're becoming more complicated over time?
Yeah, absolutely. They're becoming more metally, if you like. There's more metals being produced from, if you go from hydrogen, we only had hydrogen pretty much after the Big Bang, and then stars started getting helium, and we got more and more helium, and then they got more and more of these heavier elements all the way up through the periodic table. So that every successive generation of stars has broadly more of these metals. Of course, it depends on exactly what was in the cloud when it formed, but on average, then, you're going to get more and more metals.
It's nice to think that, you and I, we're not going to be around by that point. Like, we will have well and truly been absorbed into the Earth by then, when the Earth does get gobbled up by the sun as it expands out into its red giant phase. And so we're going to become part of that, which then gets, sent out into the nebula. So it's kind of a nice thought to think that in just several billion years, we'll be off floating through the void waiting to become part of the next interesting star. I kind of like that. That works for me.
Yeah, it's a very famous quote that we're all made of stardust because all the elements in our body were fused originally inside stars. But we can turn it around and also say that we're all going to become stars one day as well.
All right, Emily, well, I think that's probably more than enough for our first in a series of, let's call it N podcasts about stellar evolution, going from the beginning of our sun to the very end of our sun, and a really nice sort of little poetic ending there on us becoming parts of a planetary nebula. I kind of like that in the future. That works for me. That's where I'd like to end up, I think. Something to aspire to. Listen, if you would like to get in touch with us here on the show, then there's probably all sorts of ways that you could do that. Emily, how could people get in touch if they wanted to?
Well, straight away you can head to your favourite Twitter portal? Do you port Twitter?
I don't know. Whatever you do with Twitter, go and do it, and you can find us.
You can get Twitter through many ways, and
yes.
you can get Syzygy on Twitter, which is at SyzygyPod, at SYZYGYPOD.
That's correct. Have you been doing the social media much lately, Emily?
I've been avoiding putting pictures of kind of warm, sunny New Zealand up on Facebook, but I think that's
probably wise.
Heading over to the Syzygy Facebook and catching up with a few bits and pieces there. So.
Oh, good. Yeah, speaking on behalf of the rest of the planet that isn't in New Zealand at the moment, I think that's a wise course of action. Don't start showing off too much. But yeah, at SyzygyPod, go and check us out on there. We are also at SyzygyPod on the Instagrams, and you can search for Syzygy on Facebook. We're on there as well. Or you can just go to our website, Common or Garden Variety website, syzygy.fm, where you can find this episode and all the other episodes with the show notes and the pictures and all the details, all the links, all the fun stuff on there. And I should mention again that website is brought to you by our fabulous new patron, Jimmy Lee, who has ponied up the dough to keep the electrons flowing through all of our electronic property. If you want to be like Jimmy, which, like you do, who wouldn't want to be like Jimmy, then go to patreon.com/SyzygyPod. There's that thing again, SyzygyPod, where you can, if you so choose, become a financial contributor to the show. And every dollar, pound, whatever monetary type of choice you want to throw our way goes towards helping us to do what we do. And as we mentioned at the top of the show, when the world does open back up again, that includes things like live shows and festivals and just doing fun stuff like that. But if you just want to support the show in other ways, the best way to do that is just to tell everyone you know. If there's someone in your life that you think, you know what, they might get a kick out of Emily and Chris nattering on about the life and death of the sun for an hour, then tell them about it. The other thing you can do is go and leave a review at Apple Podcasts or Spotify Podcasts or Google Podcasts, wherever you get your podcasts from. Give us some stars, give us a review. It helps people to find where we are. But we're going to have to wrap it up for there. So, Emily, it's really nice to be back. Good to see you. Glad that things are still going good down there on the other side of the world. You're going to be doing some interesting stuff soon. You're going to start doing some observing runs down there. It's not all, it's not all fun and games.
I'm heading down to be on Telescope, which is really cool.
Very nice. Well, I hope that goes really well. Find out how that goes maybe next time I chat to you. Might chat to you from the telescope when I think we're going to talk about Mars. So catch us next time. Until then, Emily.
Catch you later.
Bye, everybody.